Okay, hello everybody. So today we are going to continue talking about alkenes, and this time we're going to be focused on a new mechanism to go along with SN2 and SN1. And I know we've talked about hydrogenation, so that's kind of a separate thing, but this is going to kind of fall in line with those two reactions. And so this process, what we're going to be talking about is what's known as dehydrohalogenation. And essentially what it means is removing a hydrogen and a halogen from an alkyl halide. So I've got an alkyl halide shown here. And what we see is that when we treat this compound with a strong base, which I'm just going to call B minus here, so strong base, that compounds that contain, so if this is the carbon that's next to the halogen, we refer to that as the alpha carbon. And then the carbon that's next to the alpha carbon is what we refer to as the beta carbon. So specifically, we're talking about a compound that has an alkyl halide that has hydrogens that are at the beta position in order for this to occur. And so what happens is that when you treat this with a strong base, is that you end up getting a compound where you have a double bond that forms, and this is where the beta carbon was, where the alpha carbon was originally, and we also produce a compound HB as well, okay? And let's not forget also that the halide is formed here. Now, one of the things I want you to notice about this is that if we started this reaction off with an alkyl halide and a strong base, that's two reagents, well, we end up getting three products. And so what that means is that whenever you do this type of reaction, you go from having two reactants to three products. And what that means for us is that the entropy here is greater than zero. In other words, there's now more entropy than there was before by doing this reaction. So just keep that in the back of your mind, because it's going to help explain a phenomenon that we see later about this type of reaction. So when an alkyl halide with hydrogens on a beta carbon, which we'll now explain what that is, next to a halogen, is treated with a strong base. And what we call elimination can occur. Notice I didn't say will, notice I said can there, and that means there's some factors to consider. Now, the biggest factor, of course, being the mechanism and how this proceeds. So the way I'm going to explain this is that if we look at a reaction profile of what's going on, and we originally have our compound where roll this out, and we have alpha and beta, and we have these beta hydrogens right here, and we're treating this with base B. Okay. That this is going to go uphill in energy. Okay, so we're going to go up here to a transition state, and then down here is going to be our products. Now, the products that we produce are going to be more stable than our reactants. So this is a exothermic process overall in most circumstances. But the question, I guess, here is well, what is this? What does this transition state look like at the top? What is it most closely resemble? Well, what you have is you are going to start breaking the bond between the carbon and the halogen, okay? And going to have a hydrogen here on that beta carbon. That bond is also going to start to be breaking as well as you're forming a bond to the base B, which is starting now to lose its charge, while this one is starting to gain some negative charge. And you're starting to form a pi bond between these two carbons. And with that other carbon over there. So this is kind of what's going on here, is that we're getting this type of elimination. And so this indicates that the orientation of the hydrogen is important in this overall process. But if we had to describe this to somebody, this reaction profile should look very similar to what we've already seen, and that is this is very similar to an SN2 reaction. So if you were to write out the rate law for this process, the rate depends on the concentration of the alkyl halide first order and the concentration of your base as well. Okay. And that means that this is second order overall. Second order overall. So putting that all together, you've got elimination plus second order and we describe this as what is known as an E2 reaction, elimination second order process. Okay. Now, again, like what I was saying earlier, you want to notice the rate law for E2 is identical to the rate law for SN2. Okay. So, how to promote E2 over SN2? Question mark. Well, larger bases are worse nucleophiles. Larger bases are worse nucleophiles. Okay, and that's because nucleophiles have to get behind a carbon that's attached to a leaving group, whereas a base just has to extract a hydrogen. So if we're talking about something like, if we're going to use methoxide versus hydroxide, well, methoxide is a better base, but hydroxide is a better nucleophile. Okay, and it's better because it's smaller. Okay, so one way to promote E2 over SN2 is to kind of, bulk up your base. The other thing to consider here is to heat the system. Heat the system. And the reason why that works to promote elimination, which generally will promote elimination over substitution, is because of the Gibbs free energy. If your entropy effect is positive, which it is with an elimination, well, then if you increase the temperature, that will promote this delta S term, helping to make the overall reaction or the overall free energy be negative, which is a spontaneous process. So that is a couple of things that we can do to kind of help, tilt everything in our favor towards elimination. Now, sometimes more than one possible product can be formed from elimination. Sometimes more than one possible product can be formed from elimination, as there are two or more non-equivalent beta hydrogens. There are two or more non-equivalent beta hydrogens. So, for example, if we were looking at something like this, and we were to treat this with sodium ethoxide ethanol, we'll talk about that in just a minute. One thing to note here is, well, if this is the alpha carbon, well, you have beta carbons here and here and here. Now, both of those positions are equivalent in red, but the one in blue is definitely different. Okay, so these two are equivalent, but that one in blue definitely isn't. Okay, now that means there's going to be a chance here to get two possible products. Now, this may be one of the first times you're seeing this. Hopefully it isn't, but just to kind of explain what that is, so we've got sodium, which is positively charged, and we have ethoxide, which is negatively charged, and this is common to see this written out in this form. Now, ethanol is the conjugate acid of ethoxide, and elimination will often use the conjugate acid of the base as the solvent to promote elimination over substitution. Okay, well, let's think about what we could get here. So if we treat this with ethoxide, we're going to get one possible product here, and it's going to look something like this. So again, 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5 carbons, and a bromide. Okay, and again, that was the alpha position, that was the beta position, and these are the two carbons here on the end. And don't let how I'm drawing it confuse you. This is now trigonal planar, so that's why I'm drawing it this way, not drawing it weird. So I'm trying to make the bond names all look appropriate. Now, the other possible product here is you're going to get elimination here on one of these hydrogens, and it's the same product regardless of which hydrogen you choose. And that product is going to look something like this. Okay, you've got alpha and beta here, and bromide, of course. Right. Now, I'm not saying we're producing two equivalents of bromides. I'm saying, well, overall, that represents one. But this is not a one-to-one mixture either. So it turns out that for the compound on the top, that is generally what we would see in this particular case, about a 69% yield, 60-70% yield, let's just say 70% yield, and about a 30% yield for this one. So clearly a dominant product for the one that's in blue. Okay, so now the question here, of course, is, well, why? Why is the blue reaction favored over the red reaction in this particular case? Well, that has to do with the type of alkene that's been formed. So why is one alkene favored over the other? Question. And the answer is what is known as Zaitsev's rule. Okay. Basically, Zaitsev's rule says that the more thermodynamically stable alkene, the more substituted alkene, is usually favored in an elimination. Again, see, there's some possibilities here, but we're going to have to consider some exceptions. But I want everybody to notice that, okay, this is the more substituted alkene. You've got 3 groups around the double bond versus just 2 here. And so we talked about that earlier, that the more substituted an alkene is, the more stable it is when we talked about heats of hydrogenation. Okay, so, but you can't just apply this rule blindly. There are ways to, kind of upset the apple cart and change the selectivity. So if the base is too bulky, or let's just say is very bulky, then elimination begins to favor hydrogens that are attached to the less substituted beta carbons. Okay, so if we were going to look at that compound again, that same alkyl halide, but we were to now treat this with a different base, and this time we're going to use potassium terpentoxide, and this will generally be run into butanol. Okay, that is clearly a very bulky base. Well, now the hydrogens that were down here, okay, they are attached to what I would refer to as a primary carbon, meaning that carbon is only attached to another carbon there. So these are methyl hydrogens, okay? Now, that is different from the carbon that we're seeing up here on top. This carbon here is attached to 2 other carbon groups, so I'm going to say that is a secondary carbon, just using that same terminology that we recited before. These are referred to as methylene hydrogens, but I like this secondary stuff. But it's clearly more substituted. Carbon, okay? And so this hydrogen down here on the bottom has less sterics associated with it. So that just means that the base, tert-butoxide, is going to have a little bit easier time removing, okay, that hydrogen. And so that means that what we would see in our on our product mixture this time is for the red system, which I'm going to draw it in the same place that we saw before, versus the blue system. Okay, the selectivity now is flipped. We're now seeing about a 30% yield of the Zaitsev product and about a 70% yield of the less substituted product. Now, here's just some terminology to throw in there. This is sometimes referred to as the Hoffman product, okay, named after August von Hoffmann, who studied systems like this using quaternized nitrogens, which we'll talk about towards the end of the course. But this is just showing you that you can't just blindly apply Zaitsev's rule. You have to be careful about that. There's also another place where this can occur as well, and that is with systems that contain alkyl fluorides. Alkyl fluorides are also an exception to Zaitsev's rule. As fluoride is a rather poor leaving group. Okay, and again, just remember that hydrofluoric acid is a weak acid as opposed to HCl and HBr. And so that means fluoride is a rather strong base, and that's not a very good leaving group. And charge buildup on the transition state is lower in energy in forming the less substituted alkene. So what that essentially is saying is that if we were to take a alkyl fluoride like this one that clearly has two alpha hydrogens, so we have an alpha hydrogen here and an alpha hydrogen here, excuse me, beta hydrogen, beta, slip of the tongue there. Then if we were to treat this with methoxide and methanol, you may think that, okay, it's going to want to go, this is not too terribly bulky, it's going to want to give the predominant Zaitsev product. But it turns out that what happens is that when the methoxide comes in and starts to attack that hydrogen, that the transition state that this goes through actually kind of behaves like this. So instead of the fluoride just immediately leaving, you start to get quite a bit of negative charge buildup on the adjacent carbon first as that hydrogen bond is, or as that bond to hydrogen is starting to be broken by the methoxide. And so because of that, the charge buildup is preferred on a less substituted carbon, simply because the more carbons that are on this, well, the more electrons that are surrounding that negative charge. And so this ends up being the lower energy transition state. So that means that we end up getting the following spread. So for our for our Zaitsev product in this case, we end up seeing about, well, close to about a 30% yield. So similar to what we were seeing up before. And on the Hoffman product, closer to about 70% yield because of this phenomenon. So again, two notable exceptions there that deal with alkyl fluorides and bulky bases. Okay, now the last thing I want to address here in this topic is to talk about how this happens as far as the mechanism is concerned. So E2 eliminations must occur when the molecule is in an what's called anti-periplanar conformation. Must occur when the molecule is in an anti-periplanar conformation. This is not an issue for most acyclic systems. But rings are held in a particular conformation. Rings are held in a particular conformation. So that means that you get free rotation around sigma bonds, but if it's held in a ring system, like if we're looking at one of these cyclohexane systems, let's say, well, that's not always the case, because if you look at this compound, we've got two beta hydrogens. So here's your alpha, here's your beta. So there's a beta hydrogen right here in my pencil head. And there's also beta hydrogens over here as well. Now, you would expect if you were going to treat this with oxide and ethanol, that there would be a mixture of two products here. But it turns out in this case that in this reaction, the yield, the elimination product, is almost a 100% yield for this compound. And we see pretty much virtually none of the blue hydrogen being eliminated. It's entirely coming from these two right here, or from one of those, I should say. Now, the reason for that is the chair conformation must have the hydrogen being eliminated and halogen axial to each other in order to be anti. Okay. So what that means is that if we were to go and draw out this system, then in chair cyclohexane, I'm sure you guys were thinking we were completely done with that, but this is where this starts to come back with a vengeance. Because if you've got that chloride right there, and I'm going to draw it up in axial, so that's our alpha carbon here. Okay, and then we have the blue, these blue hydrogens right here with this this tert-butyl group. Well, I'm going to draw that hydrogen, which is how it's oriented right there, it's drawn up relative to this one. And if you remember what we did, if we're drawing this axial, well, then that means that hydrogen has to be equatorial, like so. Okay. And the other hydrogen, which is over here, the other beta hydrogen, well, you have two of them. You have one hydrogen that I can draw out equatorial, but there's another hydrogen that I can draw in that is clearly axial. And this is the reason why that we see almost a 100% yield for this predominated for this particular system, is the ethoxide must attack this hydrogen in such a way so that the oxygen, the hydrogen, this carbon, and that chlorine are all in the same plane, and that those two atoms are anti to each other. And that can only happen if they are both axial to each other. And so that's what is leading to this product. Now, of course, you don't have to draw the chair out to predict this. If you had done what we did earlier, like we already know that that hydrogen's equatorial, so it can't be eliminated based on this little trick. And so you know that, okay, well, that hydrogen is going to be equatorial. Well, then this hydrogen right here must be axial. So we know that that's the hydrogen that's going to be eliminated with the chlorine. So you can predict this. Let's try this with another one. I'm going to change it up just a little bit. So now I've got this group out here. Okay, with a chlorine now. And we're going to treat this with ethoxide and ethanol. Okay, and so now, based on that, do you think there'll be a single product, multiple products? And if there are multiple products, do you think that this is going to, there's going to be a major product? Okay, so there's your alpha carbon, there's your beta carbon. So that means I should look at the hydrogens that are there. There's a hydrogen pointing towards us. So if there's this group is pointing away from us, the hydrogen will be pointing towards us. And that means over here on this side, there's going to be another carbon, and there's going to be a hydrogen coming towards us, and going away from us. Okay. Well, if this group here is pointing away from us, and it has to be axial, so you have to have the leaving group axial. Well, then that means this group here is pointing in the same direction and on the equatorial, which means the hydrogen it's attached to is axial. So that is one possible product. So I'm going to draw that guy out in black. So we've got oxide going after that, eliminating. So forming a double bond here. Notice now that I'm no longer drawing that dash because it's no longer a stereocenter because you now have a double bond there, so that's trigonal planar. The chloride's gone, and then those two hydrogens are still there, but we don't have to show those. Okay, so that is one product that we performed. Now, on this side, we know that that hydrogen is going to be equatorial if the leaving group is axial. So that means that that hydrogen that's pointing up is also axial, and that ethoxide will also be eliminating it as well. So we'll draw this out in another color. So you've got your isopropyl group here, which still has its stereochemistry. You still have the methyl group over here. And now you have a double bond right here. Okay, so now we're predicting that there's going to be two products that are produced. Now, based on what we've talked about in today's lecture, which one of those two do you think will be the major, or do you think they will occur in about a 50-50 mixture? And if you said, well, there's going to be a major one, and there is going to be a major one, and that major one will more than likely be this guy right here, as that is the Zaitsev product. And this base here is not too bulky. Okay? It's not tert butoxide. That's a primary alcohol that produced that, so that's not too terribly bulky. So you would predict the Zaitsev product, or the more substituted alkene, would be the major product in this case. Okay, now we spent the entire lecture really just going over this one reaction, but I think you can see how important it is and all the things that are having to come to bear for you guys to understand this. You have to review your chair cyclohexanes and also some of your acid-base chemistry for this to make sense. So everybody please practice a few of these. There is another elimination reaction that we're going to discuss in the next video. And I believe that we will be able to finish this this chapter probably in 2 more lectures, but we'll see how it goes. Okay, so that's it for today. So if you guys have any questions, just feel free to post a comment in the comment section, or send me an email, and I will get back with you as soon as I can. Okay, everybody, take care, and I will talk to you guys again soon. Bye-bye.